So welcome to this second part of the first lecture of wireless communication. I will try a different way of recording. We're using the iPad, so let's hope it's better than before. So last time we ended with Fourier transforms. Now we move on to convolution. So when you have a filter C or channel C, an incoming signal U, you can compute the convolution, which is Y, by solving this integral. The convolution involves two notions of time. We have time t and delay tau. So the delay tau is integrated out. We just end up with time. The frequency transform of this expression is given here. So the frequency domain, the convolution is just a product. In wireless communication, often we work with time varying convolutions, which means that the channel changes over time. So that it's shown in these figures here. So the channel at some time t1 is given by the first figure as a function of delay tau. At t2 it changes, and t3 it changes again. So this means when I compute the frequency transform of the channel, if the channel is a constant channel, C of tau, then the frequency transform doesn't change. But if the channel is time varying, C of tau and t, then the frequency transform will also change. Mathematically, not much changes. The only difference is that we have a t here, right, which is the same t as here and here. You can no longer write this nice frequency transform, Fourier transform expression, but you can still define a time varying frequency transform, right? So where for each time t, you compute CF at that time t. Good. So the first time you see time varying convolution, maybe this is a bit strange, so it's good to do a small example. So here you see an incoming signal, right, at these different times, and it's 0, 0, 1, 0, 0, so it's an impulse. And we also have a channel, so this here is the U of t. We have a channel C of tau and t, which is given by these equations. So the channel is constant up to time t, to time 2, and then at time 3 it changes, and then it takes some other value. So in other words, for t less or equal than 2, we have tau minus 1, 0, 1, 2, and the channel is 1, 2, 3, 4. For times greater than 2, minus 1, 0, 1, 2, the channel will be 0, 1, 2, and 3. All right, so now the question for you is, can you determine the output? So if you convolve the input with the channel, what is the output? And I recommend you pause your video and then try to solve this problem. Otherwise, we just move on to the next slide. All right, so we have basically two expressions. One expression for times up to time 3 or up to time 2, and one for times greater than 2. Right, and recall that for up to time 2, the channel is given by 1, 2, 3, 4. So there's actually here 1, 2, 3, and 4. And the channel tap at time 0, which is 2, is multiplied by the incoming signal at time 1. The channel tap at time 1, which is 3, is multiplied by the incoming signal at time minus 1, and so forth. And if you compute this for n less than 3, you find these outputs, so 0, 1, 2. Similarly, for times greater than 2, the channel changes. So now, let's see if I can clear something. At time 0, the channel is 1. Okay, so then we have here 1 corresponding to un. And you see here the other coefficients. You compute this for times greater than 2, and you find these outputs. Right, so as a function of discrete time t, minus 1, 0, 1, 2, 3, 4. Before time 0, there's nothing, it's just 0. Let me use different color. 0, then it shoots up to 1, at time 0 shoots up to 2. Is that correct? No, that's not correct. Go back. Still 0, goes to 1, goes to 2. At time 3 it stays 2, so now we use the other equation. At time 4 it becomes 3, and then it will go to 0 and like this. So this will be the output y of t. Good. All right. Some other basic concepts. We will use random variables which have probability density functions or probability mass functions. If they're discrete, we will often use moments. So the first moment mathematically is given by this expression. We often write it with an expectation. So maybe I can write in general, we can write expectation f of x, which is by definition integral f of x bxx dx. For continuous random variable, for discrete, it would be sum over all x, f of x bxx. This is just a general expression. One particular random variable that we'll use a lot is a complex Gaussian random variable, which consists of two real Gaussian random variables, right? So with different mean, but with the same variance. And if we add these two and multiply with the imaginary unit, we obtain a so-called proper complex Gaussian random variable, which has a complex mean. So this guy is complex, right? So mu is equal to the real part of mu, which comes from x plus j, the imaginary part of mu. And the variance is the sum of the individual variances of the real and imaginary components. Here, x and y have to be independent. So there are many variations of this. You could create complex Gaussian random variables with different variances or not independent x and y, but then they would not be proper complex Gaussian random variables. So for some lectures, we also use the Q function, which describes the tail of the Gaussian distribution, given by these expressions. Soon we'll also work with wide-sense stationary random processes. So these are random variables that change over time, but when they are wide-sense stationary, that means that their moments don't change over time. So the mean of the process is constant. Also, the autocorrelation, which tells you to what extent is x at time t correlated with x a little bit later, does not depend on t, but only on this delay difference tau. Okay, so this autocorrelation function tells you how quickly does the process vary. You can compute the Fourier transform, and this is known as a power spectral density. A particular kind of random process we will use is the wide Gaussian noise process, which has as mean mu x equal to 0, an autocorrelation function at 0 everywhere except at 0, and a power spectral density of n0 over 2. And this delta function, I guess the most important property is the following, that if you have delta tau minus tau 0, f of tau d tau, that this is equal to f of tau 0. Okay, so the delta function kind of picks the value at this time tau 0, and everything else is removed. Here's an example of working with random processes. Let's suppose you have a wide random process n of t with power spectral density n0. So the real and imaginary part each have half of this power spectral density. A filter h of t, and you should compute the output power spectral density. So you can spend a minute on that, pause the video, and then return when you are ready. Good. All right. So how we solve this is here we have the standard expression from convolution that you've seen before. So h here is the filter, n is the input, w is the output. The autocorrelation function a w of tau is given by this expression. Now note that there's this little star here, and we put this because the process is complex. Now you need to put a star. If the process is real, there's no need to put a star there. Wt, let's see where Wt here is. This is this integral h of tau n of t minus tau d tau. And then with a different color we have this guy here is the other integral h of tau prime. I think there should be a complex conjugate. Okay, let's let's say that h of tau is real. Otherwise, there should be a complex conjugate here, but I'm not going to do that for now. Anyway, there's a complex conjugate here with the noise. And then we have the expectation operator, and the expectation operator is linear, so we can push it through and we just have it here. Now we know that the noise is wide Gaussian, so this means that this is a naught times a delta function, where the delta function is given here. And now we make use of the property of the delta function, so recall that f of tau delta tau minus tau 0 d tau is f of tau 0. This will give us this expression. And then we can see that this is actually the convolution of the filter with its time inverse, and we just call this another filter g of u. Right, and you can apply the Fourier transform, and then you will find that you end up with this expression. So the output power spectral density is the input power spectral density times the Fourier transform of the filter in magnitude squared. And this is something that is useful because it allows you to generate noise with any kind of power spectral density. And this will be used in your first project. Good. Some other basic concepts on detection theory. So here we have an example where we transmit data. Ooh, I didn't want to do that. Where we transmit data. So we transmit symbols, Sk, unit energy, it's shown here. And then we multiply with some energy and we add some noise, a complex Gaussian noise with a variance n0. And now our goal typically is this problem. It's called the maximum likelihood problem, where we want to recover S from R. So you know R, you know ES, you know the noise variance, and you want to recover S. Then you solve this maximum likelihood problem, which involves the likelihood function, as you evaluate for each possible value of S and you pick the maximum. Right, so if you were to visualize this, let's say that S can be -1 or +1, then you would evaluate the likelihood function from -1 and +1, it gives you some value, and then you just pick the maximum and say most likely +1 was transmitted. And this detector is nice because it's optimal in terms of minimizing the error rate. To evaluate performance, we often use the SNR. And there's two notions of SNR. There's ES over N0, which is the energy per transmitted symbol over the noise power. There's also the SNR per bit, which is ES over N0 divided by the number of bits per symbol, right? Because the energy within a symbol needs to be distributed among those bits. The performance of a communication system depends on the constellation that you use and the signal-to-noise ratio. So this is what this figure on the right shows. So on the x-axis, we have signal-to-noise ratio as the signal-to-noise ratio per bit. On the y-axis, we have the probability of making an error. So this is also called the symbol error rate. And then here we show performance for different constellations. And you see that different constellations have different symbol error rates. So QPSK is better than 16 QAM is better than QPSK. Now this is a very important topic, so it's good to dwell a bit on this and do a simple example. So let's suppose that you use QPSK, which is this, oh no, not QPSK, 8PSK, which is this constellation here on the right. And you send, let's say you send this symbol 1, corresponding to the 3 bits 0, 0, 0. You add some noise and then you receive an observation R. Okay, so let's say your observation puts you somewhere here. This is R, has a real and imaginary part, and your goal is to find the maximum likelihood detector. Okay, so how do you recover the transmitted data from R? And a more sophisticated question is, what is the probability that you confuse the transmitted 0, 0, 0 with, let's say, 1, where is 1 here? 1 is, okay, so where you confuse 1 for e to the power j pi over 2, which is this one. So what's the probability that you send 0, 0, 0, but you actually make the decision 0, 1, 1? So spend a few minutes on this, pause the video, and then you can return to the solution. All right, so the maximum likelihood detector is given by this expression. And here I immediately give the final result, which is called minimum Euclidean distance detection. So you find the A that is closest to the observation. It is good to spend a little bit of time to try to get to that solution. So P of R given A. In this distribution, the only thing that's random is the noise, right? So it should be something Gaussian. So this is equal to P of, well, the in-phase part of R given A and times P of the quadrature part given A. And the reason here is that you have white Gaussian noise. So it's independent in the real and imaginary part. So when I write these I and Q, I is stands for in phase or real, and Q stands for quadrature or imaginary. Okay, now each of these is Gaussian, so this will be some 1 over square root 2 pi sigma squared, like this, exponential minus 1 over 2 sigma squared, Ri minus the real part of A, okay, so AI squared, times, and then the other distribution, 1 over 2 pi sigma squared, exponential, okay, same thing, RQ minus AQ squared. Good, I'm gonna run out of space, but let's do my best. Okay, so then I end up 1 over 2p sigma squared, exponential minus 1 over 2 sigma squared. And then I can write the argument as r minus a squared, right? And here I make use that the norm of a complex variable x squared is the in-phase part plus the quadrature part squared. Okay, where x is xi plus jxq. All right, so this is this density. What I do now, and this is a very common trick. The first part, I can remove it because it doesn't depend on A. The second part, I can remove it because this is a monotonically increasing function. Exponential is increasing, so I can remove it, doesn't matter. And then inside here, I have another constant that I can remove because it doesn't depend on A. I have a minus sign here, so if I maximize something negative, that's the same as minimizing the without the minus sign, so I can remove the minus sign and go to minimization, and then I just end up with this argument. Okay, so what this does at the end of the day is I have the unit circle, very poorly drawn. So I receive some observation here, and I will just compute the distance to each possible transmitted point. No, not these ones. Let's see. I compute the distance of the observation to each transmitted point, like this, and give as a result the one that's the closest. So that's probably this one. Good. Sorry for this. Right, and there's also this problem of making a mistake, and I recommend that you go through this yourself. It is not very hard, but it shows how these Q functions are used. Okay, and it depends on the Euclidean distance between these 2 points as well. So you can actually compute the probability of sending any point and making the mistake of determining any other point. Our last topic for today is convex optimization. So where we want to minimize a function subject to some constraints. Now, convex optimization is a very large topic by itself, so I can only go through this extremely superficially in one slide, because we will use this in one of the lectures of water filling. So we have here a number of ingredients. We have this is called the objective function. And this function should be convex. And a convex function in one dimension looks something maybe like this, right? So a convex function has one global minimum. This could be the f of x in one dimension. For those of you who get maybe confused, there's also this notion of a concave function. Concave function looks something like this. This is a concave function, so that has a global maximum. And for those of you who get confused about convex versus concave, the way that I remember is that a concave function looks like a cave. Good. So the function should be convex. Then you have different kind of constraints. You have equality constraints. These equality constraints should be linear. Okay, so they should be, for instance, of the form ax minus b is 0. And then you have these inequality constraints, and these should also be convex. So they determine convex sets. So one way to potentially draw this, let's say you have x1 and x2. This g of x less than 1, this determines a region of x that are valid, and this region should be convex. So this determines where g of x is greater or equal than 0, and here g of x is less than 0. Okay, and a convex region means that I can go from any point to any other point and stay within the region. A non-convex region would be something like this. X1, x2. A non-convex region would be something like this. Okay, and it's not convex because I can go from this point to this point, and I do this by not staying within the region. All right, well, why do we talk about this? Convex optimization problems are nice because you can find a global solution, okay, even when x is in very high dimensions. The way that you do this is you follow just a very kind of simple recipe. You first compute something called the Lagrangian. Some of you maybe have seen this before, which has the objective function. It has all the constraints, but with so-called Lagrange multipliers. And the multiplier for the inequality constraints has to be non-negative. Okay, so this is a new function that we're going to optimize. And we will optimize this with respect to all of the variables x, lambda, and mu. Again, these are called Lagrange multipliers. All right, how do we solve this? We just set the partial derivatives equal to 0 with respect to x and mu. We impose several additional conditions, which the first one means that, okay, lambda should be greater than 0, g of x should be less than 0. That's our original constraint. But also we have this constraint that lambda times g should be 0. And this gives us a bunch of equations, right? Maybe they are non-linear, but there are a bunch of equations here. And then we can solve for all the unknowns. And this gives us the optimal solution. I know this seems very abstract, so let's do a simple example. So let's suppose we want to minimize this function, x plus y squared. So let's see, you have x and y. Then the objective function looks something like this. It's some kind of ball, right? We want to minimize this function with this constraint. And this constraint says that x plus y should be equal to 0.5. So, and this determines a line in this here. So, okay, I'm not going to draw it exactly, but this is some line. Okay, so we want to find a solution. Well, actually, it should not go through the origin. This is some line. Okay, this is what this constraint says. And then you want to find the minimum of this function where x and y should satisfy the line. Not very trivial if you don't know about convex optimization, but now you do. So then this is how we solve this problem. Okay, we formulate the Lagrangian, the objective, the constraint. We take derivatives with respect to all of the unknowns, x, y, and mu. That gives us, in this case, a system of linear equations, which you can easily solve, and this turns out to be the solution. Okay. So please go through this in detail, and you will see how this works. Finally, if you want to use vectors and matrices, which we will use a lot, I recommend that you download this matrix cookbook. It has lots of cool stuff that you can use for the rest of your career. I think I will end with this for now. Thank you for your time, and see you for the next lecture.